Have you ever wondered how the Fortran computer language evolved? Let's travel back in time to the mid-1950s, a period of rapid technological advancement. It was during this era that IBM initiated the development of a programming language that would forever change the landscape of scientific and engineering computations. This language was none other than Fortran, an acronym for Formula Translation. Now you may ask, who were the brains behind this groundbreaking invention? The credit goes to John Backus and his dedicated team at IBM. They recognized the need for a high-level language that could translate mathematical formulas and engineering problems into a language that a computer could understand and process. This was a significant shift from the low-level assembly languages prevalent at the time, which were not only difficult to write, but also highly error-prone. And thus Fortran, the groundbreaking high-level language, was born, paving the way for a revolution in computer programming. From its humble beginnings, Fortran underwent a series of transformations. The journey began with the initial version, Fortran First, which was revolutionary for its time, being the first ever high-level programming language. But it was just the start of an incredible evolution. The next iteration, Fortran II, introduced the concept of subroutines and functions, allowing for more modular and reusable code. It was a significant step forward, but the developers didn't stop there. Fortran III was a more ambitious project, planned to include features like symbolic manipulation of mathematical formulas and automatic differentiation. However, due to its complexity, it was never released to the public. Then came Fortran IV, a leap forward. It was the first version to be standardized, making it more accessible and widely adopted. This version eliminated machine-dependent features, making the language more portable across different systems. It was a game-changer, setting the stage for the widespread use of Fortran in scientific computing. Fortran 77 marked another milestone. It introduced new features such as implicit typing and if-then-else control structures, further enhancing the language's usability. It also improved upon the standardization of Fortran 4, leading to increased adoption. Yet, the evolution didn't stop there. Fortran 90 was a major overhaul of the language. It introduced modern programming concepts like array programming, user-defined types, and modules. It was more expressive and powerful than its predecessors, and it set the standard for future versions of Fortran. In each of its iterations, Fortran pushed the boundaries of what was possible in programming. With every new version, it introduced features and improvements that made it more powerful, flexible, and user-friendly. It evolved with the changing needs of the programming community, adapting and growing to meet new challenges. Thus, from Fortran I to Fortran 90, each evolution brought forth new capabilities, making it a versatile tool for programmers. The evolution of Fortran is a testament to the continuous innovation in the field of programming, and a reminder of how far we've come since those early days of coding. The journey of Fortran has been impressive, but what about its impact on the programming world? Fortran, short for Formula Translation, was revolutionary in its time. It transformed the world of programming, making it more accessible and efficient. Before Fortran, programming was a laborious process, akin to solving a puzzle with a blindfold on. But Fortran removed that blindfold, making it possible for more people to program and for more complex computational problems to be solved. Fortran's impact is not just in the realm of programming. It has also influenced the development of many other high-level languages. For instance, COBOL, a language that dominated business data processing for decades, borrowed heavily from Fortran's syntax. ALGOL, another early high-level language, was influenced by Fortran's approach to mathematical expressions. But the influence of Fortran extends beyond just these languages. It has set a precedent for how programming languages should be structured and function. It introduced the concept of high-level languages, which are easier to read and write than low-level languages. This concept has been adopted by virtually every programming language that followed. Fortran's legacy also lies in its continued use in high-performance computing. Even today, more than 6 decades after its creation, Fortran is still widely used in scientific and engineering applications. Its ability to handle complex mathematical computations efficiently makes it a preferred choice for tasks such as weather prediction, computational physics, and aerospace engineering. Fortran's impact and legacy are a testament to its revolutionary design and enduring relevance. It paved the way for the development of many modern programming languages and continues to play a significant role in high-performance computing. Indeed, Fortran's evolution has not only shaped its own journey but also left an indelible mark on the landscape of computer programming.